1, 2, testing 1, 2. Boss, don't kick that. Madam, don't kick this, huh? Cheers. All right. Good afternoon. Oh, it's evening now. Okay, so as usual, between now and 18:45 it gets dark, so we don't need to go beyond that time. It's a very important topic, very short, but it's important that we know what it is and how it works. Okay? So we'll get into that just a minute. There's just a few things that I want to address. All right? And why are we so few today? Is there another class coming? Or wakomboka che? Wakomboka? Okay. I know, it's cool. Consistency is always a problem with people. So you begin together and people are showing up for classes, and at some point, you guys at the back are really making noise. All right, so people get comfortable. They feel like we can study on our own. Who? Temboson. Temboson. Sana repeat it. Avoiding Congo there. All right. All right. So innocent souls did not get that. If you laughed, you know where you belong. Okay, I want to address two things. One, either I never made this clear. Allow me to do that now. Class reps, I don't know how many you are, but you have no right to call me, text me at any time that you feel like. When we named one from each of the groupings, the idea is that the class reps, they come together, they agree at what point do we text me somewhere, at what time do we call. So imagine it's like a whole full day. I'm receiving 6, 7 texts, sir, are you coming? And I'm even thinking, when they're not even in class trips, they're just texting, right? No, you're not supposed to do that. Okay? Only the designated class reps are supposed to do that. But even then, I've noticed that there's a problem. So it takes me to point number 2. Last week I was supposed to have a test, not so. I received a whole text of people. Sir, people are not ready. Sir, we're not ready. We're looking forward to an extension. So I said, you know what? All right, cool. I'll let this one slide. Huh? But I'll need to correct some things. If you're going to wait up until you're ready for certain things, you never do anything in life. Trust me, I can give you another 1 month or 2 months for you to just study for this test, quiz, or whatever. You never feel ready. Do what you can. Have an open mind when you're going into an exam or a test. Bring all the stuff that you studied and just apply yourself there. So because of the disturbance that you caused last week, I no longer have got confidence in all of you guys that are so-called class reps, huh? So you're all fired. Lose my line. All of you. Sir, what's your name? Robert. Robert who?
Pili.
Do you have my line?
No, sir.
No homo, but I like you.
Thank you.
Yeah? I want you to be the class rep.
Very much like
You ready? So Robert is the only person with access to my line. If you want to find out if we're writing a test, if I'm coming for a class, talk to him. Sir, I'll be giving you money for bundles. Your row is 2 hours prior. Because you know the times are supposed to meet, right?
Yes.
A Tuesday and the what? 2 hours before. You can either call me or text me to find out. The rest, don't you dare. So Tamvera, nai. Good. So get my line. Fluid action on surfaces. All right, so let's get into it. Just 30, 40 minutes. It's a very important topic. I think if you found time to look at the past papers, there's always a question concerning to this. So the principle behind this is related to a lot of things that are in the space of hydraulics. So a very good example that I can give you is if we are designing or creating a dam, all right? So this is a dam, and usually this is called the upstream. This is where water is coming from. She's also a class rep. Okay, so where water is coming from is usually called upstream. When we meet in third year, we'll talk more about, there's a course called hydraulic structures. So we'll talk more about a dam. So water is coming this way, and of course you're impounding it. And then the downstream is where the water is going, and usually the levels are much lower, okay? But between one end of this structure and the other one, there's always a get through. You want to have water to be released to the other side. All right? So let's just call this a gate valve. So depending on how much water you're receiving on one side, you want to talk to whoever is in charge, and then you can release a bit of that water, and then you let it go that side. We know what a gate valve is, not so? So you can open it up, you can close it up, so that you can let water go through. The reason why I'm giving you this scenario is to demonstrate why this topic is very important. So, as engineers, when you're designing, you are interested. How strong should this gate be? This is a gate valve, not so. How strong should this gate valve be? You and I know that the pressure acting on a point is dependent on what? The depth, right? And there's a certain depth you can go under, let's say a C, that is not humanly possible for you to sustain with the body that you have. You would literally be crushed. Which reminds me, I don't know how many months this has been, but there was some kind of an exhibition. They were saying, well, we had found the Titanic down, right? And then this billionaire, together with his son, they built something and then they went down. See, just how deep the Titanic would be at that bottom, they knew that if we're going to get down there, it needs to be this one vessel that can withstand the pressure. So pressure always gets even stronger as you get down. But obviously, either they did not design it to the conditions that area, was in terms of pressure, and so everything just crumbled. You get the point? So as engineers, we're interested. If we are going to create a gate that won't break, regardless of the distance that we find or we want to find out exactly how much pressure is acting here. So when it comes to this topic, there are two questions that you always be asked. One, depending on how far your gate is to the surface of the water or the fluid, what pressure is going to act there? And then usually this is denoted by, it could be any letter really, but R is okay for the resultant pressure. It's pressure that you're looking for. What are the units for pressure? Pascals or kilonewtons per cubic meter, not so. Is it cube or it's a square? Engineers, okay? So this is one question that they'll ask you. How much exactly by pressure are we subjecting this gate to? And when we know as engineers how much pressure will be acting at this point, then we can design our gate just enough so that it can withstand the pressure that it is bringing. So it is not enough for an engineer to just say, you know what, we're going down 10 meters, so let's just make this plate this strong. No, it doesn't make sense. Everything has to be proven, demonstrated with figures and numbers. So we don't just design things. So this gets to be the same way. When you get into second year, I think third year mostly, we'll talk so much about if you've got a project and then you're giving us figures and numbers, we're going to ask you, where are you getting these numbers from? Is there an extract, a document that you've read, then cite it? Are we together? But you cannot just bring out the numbers. So one question is, one, can you find the resultant? What pressure is acting on that plate? Based on the depth, also based on the fluid that you're dealing with. So today it could be water. But it's not only in water that we're going to have the gates, is it? Okay? So this is one. And usually the distance here is denoted by just a Z bar here. Question number 2. This plate can be anything. It could be circular, it could be a rectangle, it could be a trapezoid. We want to find out exactly where this pressure that we have found is acting on that plate. So it's not enough for us to say, well, our plate, our gate here is a triangle, and then we're just going to say the pressure acting is here. No, it's not enough. We want to be very precise. How many meters from the surface exactly is our resultant acting? Tom Fan. That being said, these structures and these are what we're calling the surfaces, by the way, of interest. These surfaces could be, or they could range from a triangle, a rectangle, a circle, and anything. So only 2 questions they'll always ask you in that format. A very bringing down to home practical example is, when your bucket or your jerry can, do people still do this? Your bucket or your jerry can opens up at some point, like Chabo, okay? So what we're interested in is that capice of, it could be a capice, and usually you put it from inside. Huh? This capice is what we're interested in. So this capice needs to be very strong, or strong enough that no matter how much water you fill up here, the pressure due to this column won't still burst this capice here. So on a household level, we just guess. We just say, oh, okay, ka bucket in kango. So you can just find any capice, put it inside, use some, heat, and then plug it. This information is very interesting to us as engineers, because now we are not just guessing. Okay, we are designing, we are planning, and we are telling people figures of, for instance, how strong this capice is, because we know how much pressure is acting on it, and we know exactly where this pressure is acting. Any questions? So, the best way to bring people to this is just very basic. Did I even get an example here? You got a question? Yes, sir.
How do you know, like, that's why the pressure is acting on?
Like how you know? Okay, so we'll have an example, but it's centered around the centroid. Yeah. But again, it's not entirely up to the centroid, because it's dependent on where exactly I left something somewhere. Anyone who's seen an example or a past paper on this kind of a topic? No? Okay, going to create one. All right, so example one, something very basic. Anybody with a past paper? There's a very, no? Okay, no, it's fine, it's fine, it's fine. You can always create something. All right. My pesa. You found something? Let me see. There's one that I had, but oh yes, this is okay. If it's not too complicated, let me see. Okay, yeah, great. Okay, so let's write this one. I know you have it, but let's work with this. Boy, chani. So this is like, I think I prepared this one. 2015. When's I'm great Bwanje? Yeah, this is definitely me. This is definitely me. Okay, so example. Determine the resultant force. Determine the resultant force. Determine the resultant force on a 5 meters by 2 meters rectangular area AB. 5 meters by 2 meters rectangular area AB. Shown in the figure below. If you are talking, you won't get me. I'll repeat this 3 times, okay? So just relax. So determine the resultant force on a 5 meters by 2 meters rectangular area AB. So make AB capital. Oh, okay. Shown in the figure below. Full stop. Okay? Are we there? Should I repeat one more time? Determine the resultant force on a 5 meters by 2 meters rectangular area AB shown in the figure below. Full stop. Also determine the location of the center of pressure. Also determine the location of the center of pressure. Also determine the location of the center of pressure. I think Van Beek. So the figure below looks something like this. Let me draw it from here. So interested in this bit. Of course, if you find the original question, it looks something like this, but the one of interest is somewhere here. So A, B, and this is, well, let's just imagine this is water, H2O. So remember the jerry can that I drew down here? It isn't so different from this one. Thank you. So what they've given you is that this is just, imagine this is just a bucket. Okay, of course, one side is vertical, the other side is slanting. The slanting bit is also very important, because you can be given a question that is at an angle, okay? But for now, based on this question, we are only dealing with what's here. So this side of that bucket or dish or whatever it is, there is a rectangular piece, AB. Are we together? Rectangular piece, AB. Rectangular piece, AB. There's something missing, sir. Let me see. So just two questions that will ask you. Find the pressure acting on the plate. So there's a formula. We'll write it down and then figure out which parameter is working where. And then the second part is the center of pressure. Yes, over. Something missing here. Okay, no, that's fine. That's fine. Thank you. Okay. So the plate has been given as an area of what? AB, that's saying it's 5 meters by 2 meters, huh? I just wanted to have it there. So the first question wants us to find the what? Resultant pressure, not so? Is it what they're calling it? So it's up to you, whatever letters you can use. For now, I'm just comfortable with an R. So the resultant pressure, so the pressure due to the column above this plate, okay, can be gotten by the mass density of the fluid we're sitting in, the gravity by the Z bar, I'm going to explain what that is, and the area of the plate itself. Are you able to visualize this? This, I'll try to draw it in a 3D, all right? So it's something like this. So this piece sits here, okay, like that. And then it doesn't end here, it goes like that. Okay. And then the rectangular piece, the one which is sitting here, carry up somewhere and it looks something like this. Okay. So if this is a 2 meters, meaning this is our 5, not so? Are you able to visualize this? Yes. Except, and this is why drawing really comes in important. If you didn't do drawing, some figures like these will become a bit tricky. This is just from one dimension. This has just been seen from that direction. So you can't really see the 2D except the 2 meters. But you know that the area of the plate has been given as a 5 by 2 meters. And if a 2 has been given, then you can only assume that going in that side, it's a 5 meters, not so. This level of thinking is what separates you from a non-engineer. Because I've had this question given to students. Where is the 5? Or which one is the breadth and the length It's here, it's in the question. But what you're given is a 2, meaning what's going there is a 5. That's why I've written a 5 and a 2. Are we together? Okay, so the area, we know what it is. Mass density, what's the mass density? And this is assuming that this is water. Because the only way I can, not the only way, but one way I can tweak this question is I can say we're dealing with oil and it has a specific gravity of 0.8. Because you and I did properties, not so. So we can deduce mass density from the specific. That's why I say that if you miss that topic, please go back, it's not too late. Because everything that's going to come will always have a tie and a link to what we did. But for now, it's easy. It's water, so we're going to assume it's 1,000. Gravity will always remain the same. Z bar, again, you can always use whatever letters are working with you. Z bar is just a distance from the surface of that fluid to the centroid of the plate that you're dealing with. So Z bar is a movement from here all the way to the centroid, if I can call this center of gravity. So this is your Z bar. Are we together? So knowing that this is a rectangle, and you and I know that a rectangle is symmetrical, not so? Yes. What would be the distance from the surface to the centroid of a plate? Fast, fast, fast. +1, not so? Who's confused about where the one is coming from? Because we're moving from here up to here, it's a 1.22 given. But then because a rectangle going this way is symmetrical, we are free to say if this is 2, we can just cut it in half. Huh? But things change when you're dealing with a rectangle. A triangle, sorry. Are we together? Because a triangle is a triangle. And you cannot just cut in between and say half of this is equal to half of this. You can't do that, can you? So we'll have an example of something like that. Or find time to just research on how you can go about it. Okay, so when you do that, what are we getting? Who's got a, again, I can't say people with calculators. Madam, can I use that? Okay. What are you getting? Ah, great. Thank you so much for that. So multiply by, this is a 5 by 2, yeah? So this is the area. So this guy is covering the area. And then we've got the Z bar, and then the gravity and the pressure. Thank you for that. So we multiply throughout. Should be by 10. What are you getting? $217, right? Yes. 0.78. What are the units? What are the units? There's no point, but I want to make it a point. What are the units? This is pressure. There's a point here, so what does it become? Either kilopascals or kilonewton per. Are we together? So that's how you find question 1. Question 2 wants you to find the center of pressure. Center of pressure, okay, I'm interested. Let me just use H bar. This is what I remember from the time I was a student, I think. So the center of pressure, I want to work this here. Okay, can I erase this? Yes, Malem, bye. Yes, sir.
I think that was a comma instead of a point.
This one. If you're going to put a comma, then you're removing the kilo, sir. Were you there in the first class when we did the prefixes? Are we together? But thank you for raising it up, because this always confuses people. If I'm going to put a comma, then there won't be a kilo. If I'm putting a comma, it means I've divided this by 1,000, not so. Hence, the kilo is coming in. Okay? Okay, so question number 2. Center of pressure. So you can either write it center of pressure or just simply H bar. So H bar, how we get it is we say IgG, I'm going to explain what that is, over area Z bar plus Z bar. Z bar, we know what it is, not so? And the area, we know what it is, huh? This guy is the only unknown. IgG has many names to it, but one that has been put in your material is just simply the second moment of area, okay? It's called the second moment of area. And it has got units of m raised to the power 4. Imagine that. This is like in the multiverse. But at this level, all you need to know is that this is what it is. 1, 2, these are the units. 3, each and every plate that you're dealing with has got a formula of how you can find the IgG. Are we together? Let me repeat that. The only things you need to know is that IgG is known as, this is the second moment of area. It has the units of m raised to the power 4. And then 3, each surface shape. So a rectangle has got a formula you can use to find the IgG. A sphere has got its own formula. A rectangle has got its own formula. Are we together? So in your modules, if you go on page 46, these are the ones that you're seeing here. These are formulas for finding the IgGs for whatever plate that you're dealing with. Tamverana, guys? So we are dealing with, what area is this? What shape is that? So if you go in your module, the rectangle usually sits around the square as well. They're not that different. And the formula just says IgG is equal to, so AB 3 divided by 12. But then what is the A, what is the B? So if this is your rectangle, okay, this distance here is your B. And then distance here is your A. So basically just your length and your breadth. Are we together? So if you if you have this distance and this distance, it's easy to find your IgG, not so? Because we know that your B is what? And then your A is what? 5. So bring those here, and then come and say my IgG for this rectangle I'm dealing with as a plate is equal to my 5, open bracket, 2 raised to the power 3, everything divided by 12. What answer you getting? Someone punch this quickly, fast. So this is a 5, 2 raised to the power 3. 8 or 3? 3.33. What are the units? What are the units? So when you find this, you take it and you plug it back for you to find the center of pressure. So H bar is equal to 3.33 divided by, your area is what? 10 multiplied by, what was the Z bar? 2.22 plus 2.22. The first question wants you to find the pressure, and the units of pressure are pascals, not so? Or Newton over an area. The second question is they want you to find the center of pressure. The center of pressure is just a distance. So I'm expecting when you give me the value here, it should be in meters. It's just a distance from the surface to exactly where the pressure you had found earlier is acting. Tuamfana. So, center of pressure, and how you know that this is correct? Your IgG, we said, has got a unit of what? M raised to the power 4, right? Yes. What are the units for area? What is the unit for area? M to the power 2, not so. What is the unit for a distance? Just M. Huh? So you find that 3 of these guys will cancel there so that you remain with what? Just an M. Because this is also an M. So these will just be like terms. Are we together? So can someone just punch this for me? So get the denominator in brackets. Huh? No, I want you to give me just the whole thing. So divide the 22 into the 3.33. Wangu. 2.37. So 2.37. What are the units? So you can safely say that based on the conditions given, based on the plate shape, based on the size of the plate, based on how deep the plate is into the water, the pressure that can be found there is what we found earlier. And this pressure is acting exactly 2.37 meters from the surface. That information is very important to us as engineers, because if we know the pressure that will be acting on this plate, then we can design our plate to withstand that pressure. But then we go further on to say, where exactly is this pressure going to be working? Because you can just design for everything, but then where it's the weakest, that's where the pressure is. So we want to know exactly where it is. So if we know that it's going to act at this depth, then we know that we're going to reinforce. Okay? Something to think about when you're solving this question. The total distance from here to maybe here is what? So 1 point this and about 3.33. Yeah? And then you come and find that your distance is going into 5. Then you should know that you've made a mistake. Does that make sense? What I mean is that from here to there is a 1.22, not so. And then if we're going to add a 2 meters, it's going to be what? A 3.22, not so. So whatever happens, your pressure, your center of pressure should always be around the plate, within the plate. But you okaboa solve pesa that H bar ipite enda ku 4 or 5 or 10. Washapo na underline answer. Nishi wasova. So this is how we find these questions. So just 2 questions. Yes, sir.
I wanted to ask this same question. If it was supposed to be maybe done on that side, does the angle has a problem, or it's just left like that?
Nah, the angle just helps you to, and I'll talk about it the next time we have a class. What I would want for now, of course you can research further, but we'll come and talk about it. But I'd want you to get used to the fact that these plates are different. So if it was a triangle, it would have been a whole different ballgame here. And the load hinges on the IgG. So one, I would urge you to know the formulas for the IgG for a rectangle or a square, know one for a circle, and then also know one for a triangle. Usually the questions will just revolve around that space. Because in an exam we may provide, we may not. Yes, sir?
But what causes the allocation of the pressure to move from the center of the
That's a very good question. Did you get the question? No. Bafunse, sir.
what causes the pressure to change its location from the center of the plate? I said, what causes the pressure to change from the center of the plate?
Mm-hmm. Yeah. So he's saying, why the difference? If my plate is already known that this is my center of gravity, and it's only a meter down, halfway, why is it changing? That's a very good question. So a lot has to do with your second moment of area. At this level, we don't really go into how exactly it was put up. But if you go further, they will explain exactly how the center, or rather the IgG, even has a formula such as this one. But the difference usually comes in here. So experiments were done, put in different fluids, so to speak, and they discovered that for us to know the IgG, this is how it works. It differs from one place to the other, and this actually also influences, or it affects, the center of pressure. So meaning when you are now designing on the field, you're the contractor, you won't just come and say, what is the halfway of a 2? It won't work, you miss it. So go back to the IgG of a plate, because the plate upon which we are acting is affected also. Okay, Funso. So this is very vertical, and this is usually the easiest to solve. The other one, that man here, if you don't have his question, please have it, and at your own time attempt to solve the solution. But things change when you've got a plate that is slanting. And then obviously you are given a certain angle here. So what angle is here, 45 or 30? So this is the plate as well. And then someone wants to ask you how much pressure is acting here. But you and I know that pressure is always perpendicular to a surface, not so. So the way we are putting pressure here, the pressure here is now acting this way. But then exactly how, I think this distance was also given as 1 meter. So get that question from him, that's very good. Like, go back, find the questions. They'll sort of open your mind up. Even when you're coming to this class, you already know what to expect when I'm talking here. Not if you want to feel like So, go and work around, it's just the angles. You guys know Masokato, why? So, solve that question, like I said last time, individually solve the question. Yeah, I like Chris Brown, so it's fine. So individually solve that question, the other side I mean. And then if you've got a group, meet. Boy, wapeza chan. Don't just show up to a group study, you haven't done anything. You become a student even kwa main coach, the way you are here. All right? So, when I'm writing let me not even ask you that question. I'm not supposed to ask you that question. I'll get in touch through, sir, what's your name again? Robert Peary. I'll get in touch with him. He will convey the information at least a day or two before you sit for that test or whatever. All right, so we'll see you soon. Wait, don't move.